welcome everyone to this week Autonomy Talk. This is the last talk of the year. Today is a great pleasure to have with us Professor Maximilian Schiffer, who is a tenured professor of business analytics and intelligent systems in the School of Management at the Technical University of Munich. Also, Max is an associate member of the Group for Research in Decision Analysis in Canada. So something about Max: he received a PhD degree in Operational Research from RWTH Aachen in 2017, and then he spent some time as a postdoc in RWTH and also at Stanford, and that's where I met him. And so I have a small anecdote to introduce him. So Max does a lot of research in operational research, and actually he applies this research in real life and also in his life. When he was working in Stanford and where I met him, he had to choose where to live in order to maximize both being close and comfortable to the work position and also be next to the beach and to the sea, right? And so he was essentially living in Santa Cruz and leaving early morning every day to avoid the traffic. And this way he could have both the nice view and nice sea experience and being comfortably with us in the office. Okay, this joke aside, Max is an expert in operational research, prescriptive analytics, machine learning, and data science. And he applies these theoretical tools to a variety of things and fields, mainly in transportation problems, supply chain, and production networks. Now, recently has been focusing on electric vehicles, smart city logistics, autonomous systems, and interpretable machine learning. And for his work, he has received a lot of awards, starting from some dissertation awards up to best paper awards at conferences such as ITSC, Informs, or Agiforce. Today, he will present a novel state-of-the-art tool for the online control of autonomous mobility on-demand systems, which leverages machine learning and data-driven online optimization. This is a topic which is very dear to our research group, but to Autonomy Talks as a whole. And therefore, I'm very excited to hear more about this. And I give you the stage, Max.
Yeah, thank you, Jaylo, for the nice introduction. I think you've been chasing me for more than 2 years now to give a talk here, and I always had some excuse to not do it. So I'm happy to finally be here and to give that talk. So what I want to talk about today is learning-based online optimization for autonomous mobility on-demand systems. I will skip all the advertisements, right? So everybody's always hiring. There are always open positions. Whenever you're interested, you can, of course, reach out for a shared position or whatsoever. But let's dive into the topic with a little bit of advertisement. So usually you don't do the work all alone. There are some other people also involved in this work, which is from left to right, Kai Jungel, a PhD student of mine, who is a poor guy who has to implement all the ideas that we come up with. Then it's Axel Parmentier from École de Port and Thibaut Vidal from Polytechnique Montreal. And the game is as follows. If you don't like what I'm presenting, then shoot at me. If you like what I'm presenting, then give some credits to Kai, Axel, and Thibaut. So with this being said, let's start with a quick motivation. I will really keep it short because I think everybody listening knows it. So if we look at today's transportation systems and face some severe challenges with respect to externalities, so usually if you're living in a dense urban area, you spend more than 90 hours per year in congestion. 30% of this congestion is caused by cars or drivers circling around and searching for a parking spot. And if we talk about emissions, then transportation in urban areas makes up to 25% of CO2 emissions, 30% of particulate matters, and 60% of noxious emissions. So obviously, that's not so desirable situations that we want to improve. And one system that we've been discussing for a couple of years now to improve the externalities of a transportation system in cities are autonomous mobility on-demand systems. And depending on which studies you look into, those numbers may vary a little bit. If you build an average, then what experts envision is that with such systems, we will decrease travel time by up to 30%, decrease the need for parking places by roughly 44%, and decrease emissions by 2/3 of what we have today. So what is an autonomous mobility on-demand system? So basically it's Uber with self-driving cars, right? So it's a fleet of self-driving cars that is centrally controlled and that serves passenger transportation requests, so brings people from A to B in a city. Of course, there are always some pros and some cons. So the pros, we can do some global optimization when we control such a system. We can coordinate rebalancing and dispatching to make the system more efficient and to transport passengers from A to B efficiently. On the negative side, the question is still open if such systems will induce additional demand. So even if we can route vehicles more efficiently, we may have additional demand because the service is more convenient. And if overall we will see increased mileages due to demand rebalancing and so on. So we could probably debate for 30 minutes, 40 minutes, 50 minutes if you're on the pro side or on the con side and how the numbers actually look like. This is not what I want to do today. So what I want to talk about today is the control of such a system, because what we will probably all agree on is that the efficiency of such an AMoD system heavily depends on the efficacy of the control algorithm that we use to steer it. And then we can leave the question of induced demand and precise numbers to somebody else and just focus on algorithms to control such a system for today. So that's what I want to talk about. If you look into related research on AMoD systems, and there has been a lot of research from a system perspective, so usually multi-commodity flow models, relaxing integer constraints, assuming a fluidic model, and then looking at system design, overall traffic flows, and so on. So those works are usually strategic / mesoscopic and look at the topic from a system perspective. Then if you look on the control side, then we see MPC approaches. So this Alonso Mora paper that a lot of people know, where you do a sampling-based rolling horizon. Some works go for stochastic MPC and integrate some more elaborate forecasting techniques, or you have reoptimization-based rolling horizon algorithms that are smart way of greedy algorithms, I would say. Most of those works require some distributional knowledge or leverage this general rolling horizon paradigm. Of course, there are also some other works that are recently popping up on reinforcement learning or deep reinforcement learning on those systems. I excluded them here, but I will talk about that a little bit later. Then what we've also seen over the last years is something that I would call learning enriched optimization. So independent of AMoD systems, more and more researchers are asking the question, how should we combine optimization and learning to come up with better algorithms? And then the question is, should you split a prediction and the decision making, should you combine it? And if you should combine it, how should you combine it? So there has been this smart predict and optimize paper from Machtub and Grigas, where they argue that if you combine it, you should carefully select your loss function, right? So just because you make a good prediction, that does not necessarily trigger a good decision in your optimization algorithm. And the other way around, if you give me an average prediction that leads my optimization algorithm to a very good decision, then I don't really care about the prediction quality, right? So there have been a couple of discussions along those lines, how to combine learning and optimization. There are end-to-end learning approaches. There's something called structured learning for combinatorial problems. So how can we learn decisions for NP-hard problems in an offline setting? In the end, those approaches have not yet been used for AMoD fleet control. And this is what I want to talk about today. So what I want to do with you in the next 40 minutes is to talk a little bit about learning or fleet control optimization, and to understand if and how we can combine learning and optimization in a smart way to get better decisions for dispatching and rebalancing in AMoD systems. And I want to do that in a way where we can understand how we can combine learning and optimization. So I will neither evangelize a pure optimization approach nor a pure learning approach. So what will we do to understand those things? So what I will present to you is a novel imitation learning paradigm that combines classical online algorithms with some kind of surrogate problems, combinatorial optimization, and something that we call structured learning, so learning in a huge combinatorial solution space. We will tailor that to dispatching and rebalancing for AMoD fleets to have a specific application case, and then we will benchmark it against some other approaches for real-world case study of Manhattan. So before we start with this methodology, let me quickly sketch the problem setting to you, which shouldn't be too new. So what we're looking at is basically a set of vehicles. Whenever we look at it, the vehicle is at a certain location and is occupied for a certain time when it's transporting a passenger. And what we're also looking at is a set of write requests, where each write request is described by a pickup location, a drop-off location, a start time and arrival time, and the rewards that we get for serving that request. And finally, we're having some driving times to drive from a location X1 to a location X2. If we look at such a system and we want to find a solution for managing our fleets, and we're basically searching for a set of vehicle trips, one trip for each vehicle, where a vehicle trip in the offline setting is a sequence of write requests. And of course, the sequence of those requests can contain some rebalancing writes and can also contain idling at rebalancing locations, which I can just model by a request with the same origin and the same destination and so on. So if I take that static setting and move to an online setting, which is what I'm usually interested in when I want to control such a fleet, then I look at a problem time horizon with a specific start time and a specific end time. And I can utilize a point process to model write requests that enter the system sequentially. And what I will do is that I will discretize the system by splitting it into disjoint system time periods of a certain length, delta t. And for this period length, I will refer to its start as a start time ts and an end time te. What I then want to find is a control policy that takes a certain fleet state, here the y minus, and a certain request batch for system period as an input. And that gives me an action how to dispatch requests to vehicles or how to rebalance vehicles to certain areas of the city to control that fleet. What I will assume during the talk is that I will limit the action space of this policy to feasible vehicle trips. So you can just do it by filtering out request to vehicle combinations. For this policy, I am interested in a deterministic policy so far, and that's all that I need to dive a bit deeper into the problem. Of course, I'm not interested in any policy, so the objective that I will have is to maximize my total reward over the system horizon that I'm looking at. And here I can replace reward by whatever I like, right? So my reward could be, I will want to maximize my profit. I want to maximize the number of customers or requests served and so on. So depending on what you want to aim at, you can interpret the reward as a quantity that you like. The constraints that I have are quite simple. So if I assign a write request to a vehicle, I can assign it only to one vehicle. And I want to ensure time feasibility between requests. So if I assign 2 requests to a vehicle, then I should be able to finish one request before I start the other request. What I will exclude from the talk for the sake of simplicity is pooling. So just think about pooling as another decision layer in a hierarchical fashion here. So if we talk about requests, that might be solitary requests of single passengers, but it could also be pooled requests of 2 or more passengers if I already took a pooling decision on an upper planning level. So that's a problem setting that I have. So far, it's straightforward. So let's look at the algorithmic rationale that I have with which I want to define my control policy. So what I want to do is I want to learn a parameterization theta for an extended online problem instance that allows me to take anticipative online decisions to control that fleet. So how do I want to do that? I ideally want to do that based on optimal offline solutions that I can compute on historical data. And then I will hopefully come up with a policy that allows me to take close to optimal anticipative decisions. So a bit more specific, that's the algorithmic pipeline that I want to introduce. So let's have a closer look at that. So I'm looking at a pipeline that gets the system state X as an input. And then in the first step, I will create an extended problem instance. In my case, I will explain that later. I will do that with a digraph generator G. And then I will feed that problem instance, in my case, a digraph, into a machine learning layer, where I will use a predictor to parameterize that instance. After parameterizing that instance, I will forward the output of the learning layer into a combinatorial optimization layer, where I will use some kind of algorithm to calculate a solution on the surrogate problem instance. And once I have that surrogate solution Y, I will use a decoder to just map this solution to some actions that then constitutes a policy that I want to apply to control that fleet. So that's the main rationale that I have. To apply the pipeline, what I need is an instance generator G, a predictor phi to encode the parameterization of my instance, an efficient algorithm A to solve the offline and online problem of the underlying control problem, and finally a decoder D that transforms my solution on the surrogate problem to the actions in my control problem. So what I want to do with you on the next slides is that I want to walk you through all those steps. I try to do it with a lot of figures and pictures and not too many equations. And if you're interested in the equations, I'm happy to share a working paper on what we did here, as we're currently wrapping up that work. So on the other hand, I am very interested if you spot some pitfalls or some errors that we may have made. So let's start with the instance generation. So let's start thinking about how can I model this request to vehicle dispatching problem in a smart way to come up with a nice algorithm to solve it. And what I will do to model this problem is that I will leverage something that I call a dispatching graph to implicitly encode a couple of the constraints that I have. So how does this dispatching graph look like? What I will do is I will create a graph where a part of the vertices, in this case, the blue vertices, represent my vehicles. That's the point in time where I look at the problem. And then I will have another set of vertices, in this case, the yellow vertices that represents the request. So a bit unintuitively and not the normal convention that we have when we look at routing problems and we look at graphs where the vertices are locations. A yellow vertex here represents a trip from a certain origin to a certain destination at a certain point in time. And then I will create arcs in that graph in such a way that I only connect request vertices, which is other, when it's a feasible combination. So I will only connect request 1 with request 2 if I can serve request 2 after finishing request 1. And I will do the same for the vehicle vertices. So I will connect the vehicle vertices to all the requests that I can feasibly reach with the vehicle. What I then will finally do is that I will add a dummy source and a dummy sink, and I will just connect the dummy source to all vehicle vertices and all vertices to the dummy sink. Then as a parameterization, I will just add 0 weight to the arcs that point to the vehicle vertices. And then for every arc pointing into a request vertex, I will use the profit of this request as a weight on that arc. Precisely what I will later use is a negative profit. So why am I doing that? If you're looking at such a dispatching graph, what I'm doing here is that I encode a lot of the constraints that I usually have in my problem into this graph, right? So all the feasibility constraints that I mentioned earlier will be implicitly represented by the arc structure of that graph. And this graph has another nice property. If you look at it, this graph will always be acyclic, right? Since I'm also accounting for the temporal dimension here, I will always get a graph without cycles. So what I can say when I'm looking at such a graph, if you just choose a path in that graph that starts at this dummy source, it will always go through one of the vehicle vertices and it will always end in the dummy sink. So if I'm looking for such a path, this path will always give me a feasible vehicle trip if I speak in terms of the solution terminology that I used earlier. So once I have that graph and I'm looking for the optimal request to vehicle assignments or a solution to my dispatching problem, what I can do to get it is I can solve a k-disjoint shortest path problem on this graph. And then I will just take those paths and each path will represent a vehicle trip. So which request should be solved by which vehicle. And now you can see why I want to use the negative profits of the requests. So if I use the negative profit of the requests as arc weights, then the shortest path always gives me the maximum profit that I can gain or the maximum reward, and that's how I will maximize my objective when extracting the solution. So if you implement it in a smart way with Fibonacci heaps and so on, you can solve such a k-disjoint shortest path problem in polynomial time, right? So the complexity that you see here just depends on the cardinality of the arc set and the cardinality of the vertex set. And to give you an intuition on how efficiently you can use that algorithm to solve such instances, if we speak about 10,000 requests and 750 vehicles, then we can find the optimal solution in 0.2 seconds. If you scale it up and we speak about 25,000 requests and 5,000 vehicles, then we talk about 20 seconds. So if you think this in an MPC or rolling horizon setting where a few hundred requests come in, then you can solve it very efficiently with this algorithm. So those times already include the construction of the graph. So it's not that we're shifting the complexity to that part. So that's the algorithm that I have. It's polynomial. That's nice. So it allows for some efficient computations. If I go into the online problem, what I can just do is I can just do a rolling horizon approach, right? So I will discretize my horizon. For each batch of requests that I collect, I will create that dispatching graph, run my algorithm, get a solution, and then I can assign my vehicles. So that's the way I will think about it and how I want to implement this algorithm in the first place. So let's see what we have. We got our polynomial algorithm. That is nice. What we still need is an instance generator. So I tricked you a little bit by saying, let's look on how we generate the instances. But so far, we just looked at the offline instances. We still need a predictor to encode the parameterization, and we need a decoder. And this is what I will walk you through on the next slides. So if you think about the online instance generation. So the instance generation I described to you so far, this dispatching graph, it's nice. It gives us a polynomial algorithm, but it's somewhat only nice if we look at an offline problem at a full horizon. So why is this? Well, if you think about it, if we create this dispatching graph, it only allows for reactive decisions, right? So it allows us to dispatch requests to vehicles or the other way around, but it doesn't really allow for explicit rebalancing decisions. And this is something that I want to change now. So I will take this dispatching graphs that we introduced on the last slide and will modify it a little bit to be able to derive some more anticipative control policies where we can account for rebalancing as well. So the first policy that I want to introduce is what I call a sample-based policy. So what will I do to introduce the sample-based policy? So I will extend my horizon. So I still look at the periods that I will use to collect all the batches, so TS to TE. But then I will extend it for prediction horizon. And within this prediction horizon, I will insert some artificial requests. And then I can use those requests to account for rebalancing decisions, right? So I will connect them to the request vertices as well. I get some additional weights in my graph that I can learn, and then we'll see how it goes. So that's the first policy I have in mind. The major drawback of that policy is that if we use that policy, we either need an additional predictor or some distributional information to fill that prediction horizon, right? So we somehow need to get the information where those future requests will show up. The second policy I want to introduce is something that I call a cell-based policy, and it might be not so surprising that I will use it to try to mitigate the drawback of the first policy. So instead of using this prediction horizon and filling it with anticipated future requests, what I can also do is that I can fill this prediction horizon with artificial rebalancing vertices, let's say one for any region in the city where I want to rebalance some vehicles. And what I will then do as well is that I will add another set of vertices with artificial capacities to model rebalancing more than one vehicle to those regions, right? So by learning the weight between the orange vertex and the green vertices, I learn the value of rebalancing the first, the second, the third vehicle to a certain region of the city. So once I have that, this representation allows me to implicitly learn the value of rebalancing without requiring an additional predictor or some kind of distributional knowledge. What I have to do, though, if I take this approach, is that I have to look for disjoint paths that are now arc disjoint and no longer vertex disjoint, because more than one path may want to use this artificial rebalancing vertex in this case, right? So I have to split the request vertices that the requests stay vertex disjoint as well, and I need to come up with some little tricks on modifying my k-disjoint shortest path algorithm. So those are the two policies that I want to test, and we will see how they perform. All that I need then is I need to encode the graph that represents the instance to derive those policies, right? So I need to come up with the weight on the arcs of the graph. So what I need to do this is a predictor phi, and I need to parameterize the online instance. So this predictor will depend on a parameter vector W, and then I will have a feature set for each arc, such that I can then parameterize the digraph by saying, okay, the theta of a certain arc and the digraph results from the vector product between the W vector and my feature vector. So it's just a linear predictor in this case. So the last thing I need is a decoder. So for both policies, I will obtain a solution Y on the surrogate problem instance that I just introduced. I will run my algorithm and then I get a solution. But then I need to transform this solution into actions on how to actually control my fleet. So what I will do is, if I get an assignment of a vehicle to a request in this solution that belongs to the actual request batch that I'm currently handling, then I will just forward this assignment as an action. And in a similar fashion, I will rebalance vehicles if they also match an assignment within the horizon that I'm looking at. So if I would say that's it, then I would have skipped an important detail, right? So now you know the pipeline, you know all the elements that we have, the different control policies that we want to analyze. But I skipped how do we learn that theta, or better, how do we learn that W, right? So how do we learn that predictor to come up with a nice parameterization of our surrogate problem? So that's the last technical detail. So what do we do there? So I told you in the beginning, what I want to do is I want to learn a good policy by imitating optimal known policies. There's just one drawback with that. We don't know what a good policy is, right? If we look at the online problem, then we don't have an indicator on what is a good online policy that we can use here. Of course, we can apply some other control strategies and come up with some policies, but we do not really know if those are the best policies to learn from. So if we revisit the pipeline that I introduced, so we take a system state, feed it into the digraph generator, feed it into the ML layer, feed it into the combinatorial optimization layer, decode it, take an action. Then we can make the following observation. If we go one step back, so if we don't look directly at the policies and the action, but if we look at the combinatorial optimization layer, then this is the layer where I have a powerful algorithm to calculate an optimal solution. So the question remaining is, can I leverage this combinatorial optimization layer to come up with some good policies that I can use to learn my predictor? So what I want to do is that I want to compute some full information policies for historical instances. And then visually, if you want to see it like that, I can just slice this optimal offline solution into single bits that each represent the optimal policy in hindsight to my control problem. And then I want to use those slices to learn a good parameterization for my surrogate problem that then hopefully triggers my online algorithm to take a good anticipative decision. So I will solve a lot of offline problem instances from historical data, slice it into single pieces for the time horizons that I'm looking at. And this allows me to create a training data set that I will use to parameterize my instance. So what I just described to you actually brings us to the last part of the title that I didn't talk about, which is structured learning, right? So what I just described to you is we're looking at a huge combinatorial space and we try to learn something out of this combinatorial space. And this is more or less in a short definition what we talk about when we talk about structured learning. So what does this mean for our problems? What I generally want to do is I want to find a vector theta for my problem instance such that the error between the optimal solution of my training data set and the solution that I'm triggering for an online instance gets minimal. In the best case, it gets zero, but zero will of course not happen in a reasonable solution, but I'm trying to minimize that error. And how am I trying to minimize that error? So what I will minimize is the difference between the theta multiplied with the solution vector y minus the theta multiplied with the solution from my training instances, right? So by minimizing that difference, I can minimize it if I choose the thetas in such a way that I choose the same solution and then this difference is zero, right? So that's the intuition behind the structured learning paradigm that I want to apply. If you think about it in pictures, then I want to find all those weights on the arcs here in such a way that afterwards my optimization problem chooses the red arcs, assuming that the red arcs are the arcs that lead to the optimal solution. So that's what I'm doing when I speak about structured learning. There's only one problem with structured learning in its basic form. So if you think about the optimization problem on the top of that slide, and there's a trivial solution to that problem, which is if I just choose theta to be a vector of all zeros, then I will also get an error of zero, right? Independent of how I choose the solution of my problem. So what I will do to avoid this trivial solution is that I will add some Gaussian noise. So I will perturb my solution slightly, and this will help me to avoid this trivial solution and to finally learn a reasonable theta. So recalling that our predictor is linear, right? So I will get the thetas just by getting the vector product of the W's and the feature vector. I can use a Fenchel-Young convex duality to show that the resulting loss function is smooth and convex as well. And once I've shown that this loss function is smooth and convex, I can learn the W's of my predictor with some kind of numerical method. In this case, I will use a BFGF algorithm to learn the W's. Then I have my predictor. And for any surrogate instance that I feed into the predictor, I can easily come up with the respective thetas then. So that's basically what I do. If you're interested in Fenchel-Young convex duality and why the gradient is smooth and convex and so on, that's 20 pages of proof. So I'm happy to share that or to point at that if you're interested, but I will skip it from this presentation to have a chance to finish somewhat on time. So instead of talking more about the theory that we use, let's see what we get. So let's talk about the experimental design and some results. I think you all know that data set. So we applied it to the New York taxi data set, where we have roughly 15,000 rides per hour. We will, for the results here, focus on a representative hour of operation, like 9 to 10 in the morning. But of course, we also tested it for other hours and see similar results. We assume some costs. We have some historical revenue data. We have some real-world traffic data and so on. And we will look at some sensitivities. So we will vary the fleet size. We will vary the request density and stuff like that. We will choose a basic setting with a fleet size of 2,000 vehicles and 30% of those 15,000 requests, assuming that this is a reasonable amount that one operator can catch in a competition. And then we will vary it in both directions to see what that triggers the algorithms with. So what do we compare our algorithms to? We will compare it to a greedy reoptimization. So just a rolling horizon, requests come in, I greedily dispatch my requests to vehicles. Having that benchmarks puts us in the convenient spots that we can ignore all those reinforcement learning and deep reinforcement learning benchmarks because they always compare against greedy. And then they always do like 2 or 3% better than greedy, right? So by comparing against greedy, if we do more than 3% better than greedy, then we do better than the DRL approaches out there at the moment. Then we re-implemented this sampling approach of Javier Alonso Mora for our setting. We have the structured learning where we sample the future requests and then learn the weights of the graph. we have the structured learning where we just have those learned capacities by not sampling requests, but having those artificial rebalancing vertices. And finally, what we can also do, we can look at the offline upper bound, right? So this algorithm is polynomial, it scales, so we can just compute the full information policy by assuming that we know the future when we compute it. So for features, there's a long list of features. The usual stuff, right? So characteristics of locations, of requests, some ratios between reward and duration, and so on. If you're interested, I'm happy to share that list as well. Maybe one note on feature selection. The main advantage in the pipeline that we introduced, where we have this perturbation in the objective function, allows us to be completely ignorant of feature selection, right? So this Gaussian noise that I add acts as a regularization, such that by design, if I apply the BFGS algorithm, the weights of the features that are not important will be set to 0. So I have an implicit feature selection in the pipeline that I set up, which makes my life a little bit easier at this point. So let's look on what we get. So what you see here is a video of the different policies executed with the full information policy on the left, then the Alonso-Mora benchmarker as a second one, then our sample-based policy and our cell-based policy. By design, the offline policy has no rebalancing because it knows the future, right? So it just transports drives and idles. Orange dots transport, blue ones drive, green ones rebalance, and red ones idle. If you search for structural differences between those policies, what you can see is that in the sampling policy, surprisingly many vehicles idle, right? So the anticipative decision in the sampling policy seems to be okay-ish, but not super great, as we have too many idling vehicles. If you look into the two structured learning-based policies that we see, is then that you can see that the cell-based policy applies a lot of rebalancing. So I see the most green dots moving, whereas the sample-based policy, where I still sample some requests and then learn the value of catching or rebalancing to those requests, seems to catch a better balance, right? So still some vehicles idle, some rebalance, some drive, but if you spot for differences, then the pure sampling idles too much and the cell-based learning rebalances too much, and the sample-based in combination with learning is somewhere in middle ground between those two. If you look at snapshots, that's also what you see. So on the upper left, you see the offline policy, which is least dense in the center of the city and a bit spread out, whereas the sampling shows a much higher density in this center of the city, created by too many vehicles idling in the center to catch potential future requests. And then we have the two learning-based policies, which spread a bit more out. And in the static version, it's more difficult to catch the differences, but you saw the differences in the video on the last slide. So those are the differences for the policies that we apply. So what does that mean in terms of numbers, right? So what works well, what works not so well? Let's look at the profits that we get with all policies for different vehicle fleet sizes. So for the base case, where we have 30% of those 15,000 vehicles and 2,000 vehicles, and then we increase or decrease the number of vehicles. So what I'm mostly interested in is that elbow here, right? But what I can also see is if I look into artificial cases with very few vehicles, then the degree of freedom of controlling something or matching something at all reduces. So the gap between the offline bound and all other algorithms gets smaller. And I see a similar effect for a different reason when I increase the fleet size, right? So I can always, to some extent, offset a bad control performance by increasing the fleet size if there are just way more vehicles, and there's always a vehicle close by that can be dispatched to a customer. So to shed some more light on it, what I want to look at is the relative performance increase or decrease between the sampling-based approach the sample-based learning and the cell-based learning compared to the greedy, which is often taken as a baseline in other papers as well. And what you can see here is that the structured learning combined with sampling the future horizon outperforms both other algorithms, right? So with this sample-based learning, I improve up to 13% above greedy dispatching. If I do the cell-based learning, it's also robust. It's always better than greedy, but the amplitude is much smaller. And what we interestingly see for the sampling approach is that as long as I stay in a reasonable regime for the number of vehicles with respect to the number of requests, then it also outperforms or matches greedy. But if I go into extremer regimes where I have way too many vehicles or way too few vehicles, then a pure sampling-based approach that does not allow for this anticipative learning decisions may even perform worse than greedy. Saying here, we tried to make the sampling as good as possible. So we even did Laplacian smoothing and stuff like that to erase some outliers and to give some advantage to the sampling, but still that's the results that you get afterwards. How does it look like if you change the objective? So if, for example, instead of maximizing profit, you just give a profit of 1 to every request in order to maximize the number of requests served, then we see a similar behavior for 1,000 to 5,000 vehicles. So again, the sample-based learning outperforms the other approaches with one difference that we see here. So if here we go to really artificial cases where we just have 100 vehicles for 2,000 or 3,000 requests, then the sampling performs quite well. So in this case, you don't have any chance to learn any anticipative, right? So in the case where you just make a number of requests, it doesn't really matter which request you catch. So in this case, as long as you sample something and dispatch some vehicles, as long as you hit a request, you do better than the other algorithms, right? That's the intuitive explanation for this outlier of the sampling suddenly being so much better than all the other algorithms, which in the case where you cannot learn anything anticipative, just match the greedy policy. Now you could say this guy shows me 5 data points and then claims that this sample-based learning is better than the other policies. So we can play that game a bit further, right? So we can fix the vehicle fleet size to 2,000 vehicles and then vary the request density. So increase the number of requests from 30% of those 15,000 to 40, 50, 60% and so on, or decrease it towards the other direction. And we see a similar trend, right? So if we increase the number of requests, so basically the resource that we are controlling is getting scarcer, then the more value we get from learning those anticipative decisions, and the sample-based policy reaches improvements up to 15%. And of course, if we go into the other direction, at some point, we do even worse than greedy because the settings that we have is too scarce to learn anything at all. What is interesting here, and that's why I like to show this additional result slide, is that all the other results give you the impression, okay, the sample-based learning, it's always dominant. But actually, if you talk about robustness, then what is most robust is the cell-based learning. So the cell-based learning, even in this artificial case where you have very few requests and 2,000 vehicles, it manages to perform better than greedy. It never performs much better than greedy. It's always only 1, 2, 3%, but it's robustly stable. Whereas if you go into this corner cases where you have a very huge imbalance between requests and vehicles, then the sampling-based approaches are screwed. And in some sense, our sample-based learning still basis on sampling, right? So that there is a tipping point where the learning cannot make up for the error that the sampling may make. Okay, a last slide on results. So I motivated this talk partly by saying, okay, you need to get a more sustainable system. So let's look at some indicators for the externalities that we create with such a system. For example, let's look at the increase of the average kilometers driven per vehicle, or at the increase of the average kilometers per request compared with the naive benchmark. And what you can interestingly see here is that although the sampling-based learning performs better than the sampling in terms of profit or number of requests, it stays below the average mileage driven per request compared to the sampling. Of course, this will go up if you serve more at some point, right? So there's no way to get below greedy if you serve more requests. But at least if we compare it to other control policies, we have a slight win-win where we can say, okay, we serve more requests, so we generate more profit, but at the same time have fewer kilometers per request or per vehicle driven in this setting. Okay, with this, let me conclude. So what I showed to you today is a somewhat novel imitation learning paradigm, right? I didn't invent imitation learning. We applied it to those online control strategies for the first time. We tailored it to vehicle routing and dispatching for AMoD fleets and benchmarked it against other state-of-the-art algorithms on a real-world case study. And what we can see is that we can outperform those approaches by up to 15%. Maybe some closing remarks that are not on the slide. So if you think about what I showed to you, then this is somewhat very counterintuitive towards everything that you will read in any stochastic optimization book, right? So no matter which stochastic optimization book you open, you will find some paragraph where the author writes you shouldn't use anticipative policies. And what we see here is that in this case, the anticipative policy works better than other approaches. That there are basically two reasons for that, right? The first reason could be we are way off from a good solution at all, and this is why it works well. Or if we look at a control problem where the number of dimensions is high enough, then maybe anticipative policies are not as bad as we thought. And if you followed this NeurIPS dynamic routing challenge, there a team of my students won following a similar approach. And there we also used those anticipative policies, and there we also had an oracle for the best offline solution. And we could show that we were only 4% off from the best offline solution. So I don't want to evangelize this kind of imitation learning or structured learning in online control, but at least during the last months, we found more and more cases where these policies tend to work well, but we still have a long road to go to understand why they work so well, right? Because it's a bit counterintuitive to what we learned so far and learned on other problem instances. With that, I'd like to conclude, and I'm happy to answer any question or to get any input on the last statement that I made.
Thank you very much, Max, for a great talk, a lot of insights. Let's open the stage for questions. So you can either unmute yourself and raise your hand, or you can write in the chat and I will read the question for you.
May I start with
yes.
a couple of questions?
Go ahead.
Thank you, Max. First of all, it's a very, very interesting work, and very timely. First of technical questions, just for me to understand. So, if you go to the slide where you introduce that z stochastic variable, right? So to avoid the zero, the trivial solution.
Yes.
Right?
Yeah.
Is the solution affected by the, by the statistics of z, or not? It's just something that disappears. The effect is
it disappears. So the trick is to choose the z from a Gaussian distribution which has a minimal amplitude. It just adds a small noise. On the actual features.
To remove the trivial solution, essentially.
Exactly. Yeah.
Mm-hmm. Okay. Now, how do you choose the? When you sample the the orange, the orange.
Yes. Yeah.
Where do you sample it from? What is the distribution that you sample from?
So what we did is we took the historical requests that we have, and then we sample directly from the requests.
Okay. And
so you could think of, go ahead.
That's what I thought, right? So, but now then what I was thinking of is what you see from the actual realized requests, right? The realized requests, of course, are, you know, a set of requests, right? And then, but, you know, you can think of how that particular instance compares to the distribution, right? To the, for example, from the expected number of requests and, you know, things like that. Now, would deviations in the observed realized requests from the expected requests, in a sense, or from the statistics, be incorporated in any way? In a sense, if you saw more requests or in different places than in the historical data, would this influence in any way how you do the future sampling, right? I'm asking this because what we found, I don't know if you ever came across it, you know, one of the most successful rebalancing methods that we found was the what we call the +1 policy, which is totally model free, right? And essentially what we say is, if every time you see a request, send one more card. And that was due to some autocorrelation in the requests, right? Meaning that if you have people who need the car there, chances are there will be more people who need the car there, right? And in a sense, that is model free. In what you have, you're only historical, based on the historical model, and you're missing on the autocorrelation in a sense. So is there a way that the two can be combined? Okay.
Yeah. That's a very interesting question, and we had quite some discussions on how to do that sampling. I think if this +1 strategy works well, will depend a lot on the structure of the data that you have, right? So if you have like a dense data set, it works well. If you have a data set with a lot of outliers where the autocorrelation is not so high, it may work less well. What we at least tested is having something stronger than a sampling. So instead of sampling or doing this +1, you could also use a deep neural network or graph neural network to do a smarter prediction. So that we tested, and the results were the same. And then in the end, we said, okay, let's apply Occam's razor. Let's not make it more complicated as it must be, and let's go with the sampling to explain that pipeline. Of course, the autocorrelation you just described would probably be a very powerful feature when it comes to the learning of the thetas. So to be honest, I never thought about that, but that seems like a very smart idea to improve the method. So that would be the easiest way to incorporate it, right? By giving that as a feature to the learning as well.
Okay, thank you.
Thank you.
I'm sure that that there are others who also have a few questions to answer, to ask.
Thank you, Emilio. Yes, let's see. Is there any other question from the audience? Shy. Actually, I have a small question, maybe to break the ice a bit. Which is, in the beginning, you said let's not focus on analyzing pooling, because that's just an instance, just a slight modification of what I'm going to introduce. And now I was curious, could you include pooling in this work? So where is it that it complicates things?
This is what Kai will do in 2023. So that's the next thing we will look at.
Okay.
So the interesting question here is, from my perspective, should you integrate the pooling, or can you keep the hierarchical perspective, right? So you remember that purely theoretical paper with this online hypergraph matching, where we say, okay, a pooling is a hyperedge in that hypergraph, and then if you maximize that matching, then you get a good pooling. but well, we proved some bounds, but we never answered the questions how to come up with the weights for those hyper edges, right? So straightforward push with what we've already seen would be to say, okay, let's learn the weights of those hyper edges with a similar logic, and then let's use this as an online algorithm. I'm not so sure if that will work well, because what you leverage when you do that structured learning is that you combine this power of learning with the structural knowledge of the solutions. And this works well if you just cut the offline solution into pieces for the online solutions. But if you now do this once for the pooling and once for the dispatching, then you're cutting the structure. You're not just cutting the instance, you're cutting the structure of your problem, which is basically what you want to avoid. So we are still discussing a good way to learn those decisions in an integrated model then, right? So then the question again is, what is a good instance representation? How should your surrogate model look like? And how can we learn that effectively? And so far, I don't have an answer to your question, but it's definitely an exciting question to follow up and to see if this methodology also works well there.
Very cool, very interesting. Thank you.
And there you can also, if you just to comment on Emilio's comment, which really makes me thinking a lot now on this autocorrelation. So one discussion that we have with the pooling is what do we gain from pre-booked requests, right? If you think about the autocorrelation and pre-booked requests and this kind of learning question, then in a wider context, then you might come up with something very smart.
Nice. Any other question from the audience?
If you invite me close before Christmas 23, I may have an answer to the pooling, right? So
exactly. Now we made the promise.
Put some pressure on me. You will directly invite me again. Then we have to solve it quickly.
Let's do it. Let's do it. I thought I saw a raised hand, but I don't know.
Yeah, or I'm unmuted myself.
Go ahead, Mark. Go ahead.
All right. Yeah, thank you for the talk. I thought it was very interesting, and especially the learning-informed optimization approach was very nice to hear about. Two things that I am curious about is, once you showed a graph where by adding the number or by increasing the fleet size, you increase the profit, which was, yeah, I guess, yeah, exactly that one. Now, does that hit a limit somewhere, or is it, did you consider the cost of the car as well? I would imagine at some point, of course, if you keep increasing the number of cars, depending on where they are located in, in space, of course, you'll have an available car nearby at some point, right? But then you have the cost of the car that you need to consider. Was that considered here, or do you see a tipping point or something?
No, good catch. So we just focus on operational profit here. So if you see at the upper line, so the dark blue one, this is the offline solution. This is, we just take the full instance, assume that we know all requests, and then maximize the profit. And then what you can see is that you reach a tipping point for 2,000 vehicles, right? So if you take those 30% of all requests, with 2,000 vehicles, you get the maximum profit, and afterwards it remains constant.
So there it should start to drop down afterwards, then you say, maybe.
Yes, yeah. If you would account for vehicle costs, then that should be the tipping point.
Yeah.
In our case, we said let's focus on operational profit, but that's also how we selected the base scenario, right? So we said the base scenario has 2,000 vehicles because in the offline setting with 2,000 vehicles, we can serve the maximum number of requests. And then since we're neglecting vehicle costs, what you then see is that you can trade algorithmic performance or how close the online algorithms get to the offline solution by just adding more vehicles, right? So that's why for 3,000, 4,000, 5,000, then the online algorithms get closer to the offline limit.
Yeah, okay. Yeah, I wanted to just to clarify that part. And the other part that made me curious was that the offline algorithm doesn't rebalance. Now, I do understand if you if you optimize only for profit, and you assume that customers will wait forever, as in don't leave the system or so. I understand that can work out, but here maybe as to hear your input, how do you think this would work if you had a customer loss assumption here, that people were willing to wait only for a certain amount of time, then drop?
Let's say the offline algorithm implicitly rebalances. That might be the more appropriate answer.
Mm-hmm.
So if you know all customers up front, then there's no need to explicitly rebalance, right?
Yes,
so you can
no.
after.
Yes.
So think about it like after serving a request, you can directly assign a request, even if it's like 30 minutes in the future.
Okay,
And
the car would start driving immediately, you say.
Exactly. So it would just drive there and wait there.
Okay.
And then, I mean, in the video, we didn't separate those things, right? So we could have split the blue dots in the offline into blue and green by saying, if there's more than 50 minutes lag for a blue dot when arriving for the next request, we make it green because obviously it rebalanced there.
Mm-hmm.
But we just skipped that,
I
right?
see. Yeah, I was wondering whether the car would start driving sort of immediately or, at some point in time, thereby making wait times possibly longer. Do you have a graph of like the wait times of how that compares, like the different algorithm? That would be like the service level would be something I was curious to.
Yeah. So I just have it for the online algorithms here. I unfortunately I don't have it for the offline algorithm here.
Mm-hmm. Did I miss it? Maybe? Yeah.
The service level, you get it, for example, when you look at the number of customers served, right? So there you can even maximize the service level.
I see. Maybe I was not. Yeah. Okay. Yeah. But from the service, I was referring to the. I mean, among others, maybe to the waiting time for each customer, and what are the as in the customer service level. Yeah. Sorry for that. Wasn't clear.
So what we do is that we assume the request enters the system with a specific start time that is requested. And if you cannot meet that start time, you lose the request.
Mm-hmm.
So all the solutions that you see have 0 waiting times.
Okay.
And then what we said, we have like a dispatching interval of 30 seconds. So what you can do if you want to model waiting times, you could just reinsert a request in the next batch again. Right. So say you cannot hit a request in the first batch.
I see.
But the customer is still in your system, then you just insert the request again in the next batch. So that's how we treated it.
Okay, so it does the simulation. Maybe I am misunderstanding this, but does the simulation dispatch a car? So if there is a request popping up somewhere, you assign a car and it starts driving, and the time from where the car started driving until it reaches the request would be what I would have considered, the waiting time of the customer. So the time from when I say I want the car and when I get the car. And then, of course, different algorithms will lead to different outcomes on that scale, right?
Yes, exactly. Yeah, this is something I don't have a figure right now, so I would have to look it up.
Mm-hmm. Okay. All right. Yeah, I think that were the two, main points that I was curious about. Thank you for addressing these.
Thank you.
Thank you for the question, Mark. I saw that Florian, actually from Munich as well, is asking, so max waiting time is given by maximum network travel time. I think this question has been answered now by answering Mark, but if not, Florian follow up with another question. Maybe I have another closing question. I'm sure you've been thinking about this, but definitely I do not expect a precise answer, just an insight. I know you've been working a lot on the interactions of different mobility providers, for instance, with game theory and so on. And so I was wondering, since this approach, for instance, leverages data, have you thought about ways in which multiple providers, knowing each provider is using such an approach, could influence each other or could compete against each other for instance, by falsifying data, or, you know, for instance, I can perform certain requests. I can satisfy certain requests in a certain way because I know that people will use such an approach to control their fleet in turn, right? And so you have kind of a competition of multiple services. What's your take on that?
I can send you 3 papers from a student of mine who recently finished her PhD on this question in a slightly different setting, where we worked on it with TomTom for charging station search. So not for dispatching requests, but for a similar setting where you have vehicles requesting a charging station in a city and then vehicles competing for charging stations. And there we worked on our coordination strategies if you manage multiple vehicles, but also on our mechanism design approaches to incentivize different platforms to even share requests to reduce local congestion. So you can think about it from a collaborative perspective and think about mechanism design to steer the system towards a more socially optimal solution. A question where I don't have an answer yet, but I think it's a very exciting one, and we're discussing it a lot these days because we're filing a larger proposal on this, is this question on algorithmic collusion in this setting, right? So what happens if more and more players choose algorithmically or data-driven strategies and they compete with each other? So what we know from stylized examples is that in this case, I end up in equilibrium points that are not the points I want to end up, right? I may end up in a similar equilibrium at a much higher price. Sometimes I may even get a chaotic behavior or oscillating behavior, and I don't even recognize it because everybody's running those algorithms. So I think if you're pointing at that, that's one of the big questions currently going around. So like Michael Jordan in Berkeley is working on it. Some people are. So more and more people are seeing that problem and start to discuss it in different settings, in stochastic games, but also of course, in larger control problems. And yeah, we're digging into that question, but we recently started. I think then you have to invite me for Christmas before if you want an answer on that. I will not manage to get that by 23.
Okay, so we have already two appointments, 2023 and 2024. That's very good. Thank you very much, Max. I think we can postpone other questions to offline. So you see Max's email here on the slide. You can reach out to him. I'm sure he is willing to interact. Thank you again for the great talk and great insights and for the time. I will follow up with the recording once it's been edited.
Perfect. Thank you. And thank you for the invitation and taking time to listen.
And thank you all for participating. And this closes the year. We are going to resume Autonomy Talks after a short break, January 10, with a talk actually again from TOM, from Matthias Althoff. So I wish you all a great break and see you all in a couple of weeks. Bye-bye.
Bye.